Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Nikolai Ivanovich Lobachevsky, 1826, presented on the hypotheses on which geometry is based, a work that challenged the very bedrock of mathematical understanding. Geometry, for millennia, had been synonymous with the system codified by Euclid. Central to this structure stood the parallel postulate, a statement seemingly obvious yet stubbornly resistant to prove from Euclid's other axioms. The postulate asserts that, given a line and a point external to it, precisely one line can pass through that point parallel to the given line. Generations of mathematicians, armed with ingenious constructions and impeccable logic, failed to derive it as a consequence of the remaining Euclidean axioms. This persistent failure, rather than discouraging inquiry, fueled an increasingly radical question: what if the parallel postulate was independent, an axiom unto itself? Lobachevsky dared to explore this uncharted territory. He embraced a counter-assumption supposing that through a point external to a given line, multiple lines exist, each diverging from the given line by such a degree they never intersect. This was not a mere whimsical departure. Lobachevsky embarked on rigorous exploration of the logical edifice erected upon this alternative foundation. This was not about simply discarding an axiom. It was about constructing an entirely new, consistent geometry. The intellectual environment surrounding Lobachevsky teemed with both anticipation and trepidation. Jerome Sacchi, centuries earlier, had attempted to prove the parallel postulate by reductio ad absurdum, assuming its negation. Sacchi considered two scenarios where the parallel postulate fails: one where the sum of angles in a triangle is greater than two right angles, and another where it is less. He successfully refuted the former using Euclidean tools, but the latter proved more elusive. While Sacchi believed he had ultimately dispensed with this hypothesis also, his struggles inadvertently highlighted the possibility of a consistent geometry lacking the parallel postulate. Similarly, Adrien Marie Legendre made significant attempts to prove versions of the parallel postulate. His work inadvertently highlighted the potential independence of the postulate from other Euclidean axioms. These efforts, while falling short of their intended goal, created the intellectual space for considering non-Euclidean options within on the hypotheses on which geometry is based. Lobachevsky meticulously traced the implications of his alternative postulate. One central concept arising from this postulate is what he termed the angle of parallelism. Given a line and a point exterior to it, the angle of parallelism is the acute angle formed by the perpendicular from the point to the line and the line passing through the point that is parallel to the given line in this new geometry. It is important to remember that in Lobachevsky's geometry, parallel has a different and more intricate meaning than in Euclidean geometry. The size of this angle depends on the distance between the point and the line. The smaller distant, the larger the angle, and conversely, the larger the distant, the smaller. A crucial consequence of Lobachevsky's geometry, and one that sharply distinguishes it from its Euclidean counterpart, concerns the angular sum of triangles. He demonstrated, through purely logical deduction from his axioms, that if the parallel postulate fails, then the sum of the angles in any triangle must invariably be less than 180 degrees. This seemingly innocuous deviation has profound implications. In Euclidean geometry, the angle sum is always precisely 180 degrees. Lobachevsky's alternative opened the door to a geometry where this fundamental property no longer holds. The initial reception of Lobachevsky's ideas was lukewarm, to say the least. His work challenged deeply ingrained intuitions regarding the nature of space. The prevailing view, influenced by Kant, considered Euclidean geometry as an inherent property of human perception, an a priori truth rather than an empirical observation. To suggest that an alternative, equally consistent geometry could exist seemed almost heretical. Despite the skepticism, Lobachevsky pressed on, tirelessly developing the consequences of his geometry. He calculated areas and volumes, explored trigonometric relationships, and probed the properties of curves and surfaces. He discovered that the circumference of a circle grows exponentially with its radius, in stark contrast to the linear relationship found in Euclidean geometry. Furthermore, triangles, even those with sides possessing extremely long lengths, will always contain an angle sum less than 180 degrees. It is important to emphasize that Lobachevsky's demonstrations stemmed from purely logical deductions, a testament to his intellectual courage and mathematical prowess. It is also worth noting the subtle but significant influence of Carl Friedrich Gauss, who, although remaining unpublished in the area of non-Euclidean geometry, had independently considered similar ideas. Gauss recognized the potential for geometries beyond the Euclidean paradigm, but he was reluctant to publish his findings, perhaps anticipating the inevitable controversy. Nevertheless, his private communications and encouragement likely fortified Lobachevsky's resolve to pursue his revolutionary ideas. On the hypotheses on which geometry is based, therefore, represents a watershed moment in the history of mathematics, a daring leap into the unknown that challenged the foundations of our understanding of space. Its initial reception may have been muted, but its long-term influence proved utterly transformative. This work laid the foundation for a revolution in mathematics and physics that continues to resonate. Lobachevsky's 1826 treatise on the hypotheses on which geometry is based initially encountered considerable resistance. The established mathematical community, deeply entrenched in Euclidean thought, struggled to grasp the implications of a geometry where the parallel postulate did hold. This postulate, a cornerstone of Euclid's Elements, asserts that, given a line and a pointer line, there exists a single line through the point that never intersects the original. Lobachevsky dared to challenge this, proposing that multiple lines could satisfy this condition. This divergence may appear minor, but its ramifications are profound. In Euclidean geometry, the sum of the angles in any triangle always equals 180 degrees. In contrast, Lobachevsky's hyperbolic geometry dictates that this sum is always strictly less than 180 degrees. Furthermore, in Euclidean space, the circumference of a circle equals 2 times pi times the radius. In hyperbolic space, the circumference grows exponentially as the radius increases. The initial reluctance to embrace Lobachevsky's ideas stemmed partially from the lack of a concrete model. His geometry existed as an abstract system of axioms and theorems, a purely intellectual construct divorced from tangible experience. A breakthrough arrived with the work of Eugenio Beltrami, who, in 1868, provided the first concrete model of hyperbolic geometry. Beltrami demonstrated that Lobachevsky's geometry could be realized on a surface of constant negative curvature, specifically a pseudosphere. This model offered a visualizable interpretation, helping mathematicians overcome their initial skepticism. Beltrami's model was instrumental in bolstering acceptance, however. It was still an imperfect representation. The pseudosphere has singularities, limiting its ability to fully capture the global properties of the hyperbolic plane. A more complete model came from Henri Poincaré, who developed 2 models, the Poincaré disk model and the Poincaré half-plane model. These models represent the entire hyperbolic plane within a disk or half-plane, respectively, preserving angles but distorting distances as one approaches the boundary. These models permitted mathematicians to visualize and manipulate hyperbolic geometric concepts with greater ease. This, in turn, fueled further investigation. The development of non-Euclidean geometry had a transformative effect on mathematics. It shattered the notion that Euclidean geometry was the sole possible geometry, demonstrating that consistent axiomatic systems could be constructed independently of empirical observation. This revelation spurred the development of abstract algebra and set theory. It emphasized the importance of logical consistency over intuitive appeal. One of the most significant consequences of Lobachevsky's work was its influence on Bernhard Riemann. Riemann generalized the concept of curvature, developing a geometry that applied to spaces of any dimension and curvature. Riemannian geometry became the foundation for Einstein's theory of general relativity, which describes gravity as the curvature of spacetime. Without Lobachevsky's pioneering work, Einstein's revolutionary insight into the nature of gravity may never have emerged. Lobachevsky's geometry provided the initial intellectual framework for understanding curved spaces, which Einstein then applied to the physical universe. Lobachevsky's ideas extended beyond mathematics and physics, penetrating the realm of philosophy. Immanuel Kant argued that space was an a priori intuition, a fundamental aspect of human consciousness that preceded all experience. Lobachevsky's work challenged this notion, demonstrating that different geometric systems could be logically consistent, suggesting that our perception of space was not necessarily innate or absolute. This challenge forced a re-evaluation of the foundations of knowledge. The lineage from Lobachevsky's initial ideas is easily traceable to modern applications. Hyperbolic geometry finds use in computer graphics, particularly in rendering scenes with wide fields of view. It also has applications in network analysis. The hierarchical structure of the Internet, for instance, can be effectively modeled using hyperbolic space. Lobachevsky's 1826 treatise stands as a pivotal moment in the history of mathematics. His work demonstrated the possibility of consistent axiomatic systems, independent of empirical observation. While initially rejected, his theories revolutionized mathematics. His geometry challenged prevailing philosophical views of space and geometry, leading to a re-evaluation of the foundations of mathematics.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.